Okay, so shall we get started? So today speaker is Chiu from Imperial College. So he's going to be here only for a day and a half. So if you want to talk to Chiu, today is the chance.
But he's coming back.
I'm coming back for twice more. But thank you very much for having me here. So as I said, I'm currently on sabbatical at the Institute of Cancer Research in London. But from October onwards, I'll return back to my home institute, Imperial College, where I run a theoretical biophysics group in the Department of Bioengineering. So needless to say, I spend most of my time. So this I'm a theoretical physicist by training, so thank you very much for having me in this program. So in the Department of Bioengineering, I run my group. The name of my group is Universality in Biology. Now, it doesn't mean that we are only interested in universal things that apply to all biological systems, but rather universality here is more in the physical context, universality in physics, where it basically means that there are many very simple tractable models that apply to a very wide class of problems. So we believe that the same applies in biology. We can find simple tractable models that apply to a wide range of biological systems. Furthermore, we, as a group, strive to expand both the horizons of biology and physics, because we think that biology is a fertile ground for novel physics, and at the same time, we do need those novel physical theories to understand emergent biological phenomena. Now, at this point, I should emphasize that you should feel free to interrupt me at any point. I think it will be a more interesting experience for all of us involved to have as many discussions along the way as possible. Okay, so by way of introduction, let me say just one slide. In one slide, what the three key biological systems my group is interested in. So on the left, we are looking at protein amino civilization implicated in a lot of human diseases. Specifically, we are looking at A-beta peptides forming these biopolymers that are implicated in the Alzheimer's disease, right? So the biology here is neurodegenerative diseases. The novel physics we need to understand that is the living polymerization, biopolymer self-assembly in a highly non-Euclidean situation, such as in our brain. The middle movie here, what we're looking at is a C. elegans embryo, 50 microns across. So C. elegans is a roundworm, tiny roundworm, but we're looking at a zygote, a one-cell embryo, and the green blobs there are the so-called P granules or gem granules, and they form via phase separation. So the realization that since this landmark paper in Science in 2009, the realization is a key organization principle in almost all cell types, revolutionized cell biology. So the novel physics we need to understand this system is, well, phase separation in the non-equilibrium regimes. We know thermal phase separation very well, not so well in the non-equilibrium regime. We can understand this really exciting emerging field of research. And also there's a workshop here in this institute in October, and if you want to learn more about this exciting area, join this workshop. And lastly, my group work a lot on active matter. What we're looking at here is an active vertex model simulated by a PhD student who since graduated, Andy Killen, is mimicking a tissue, a confluent tissue, which we'll see more. And this talk is about active matter. So remind you, the title of the talk, Polar Fluctuations Lead to Extensile Nematic Behaviour in Confluent Tissue. So the plan is, first of all, for me to define the problem, because there's a conundrum, there's a disconnect between microscopic understanding and understanding that I will elucidate soon. And then I'll introduce the tissue model that I claim to be universal, that I will use to resolve the problem using the tissue model at the linear level And lastly, I just give a summary and outlook. And this is all based on this recently published paper in PRL. Okay, before I dive into the contents, let's acknowledge the people who did the work. And this is Andy, who's graduated, a PhD student co-supervised by Thibault in the math department at Imperial College. And I thank the funding agencies that support us in the past and present. Right, so what is the problem? Right, so there are three key concepts. Some of you are very familiar with them, but I will go through them in reverse. So the three key words are polar fluctuation, what are they? Extensile Nematic Behaviour, what is that? Confluent tissues, what is a confluent tissue? So I'm gonna go from start with confluent tissue, then extensile nematic behavior, and then polar fluctuations. So the confluent tissue is a dense gapless collection of cells. Now, such as MDCK epithelial cell layer, it is basically a monolayer of cells, usually on the substrate. And this is kind of like a mimicry of that. Now, for the real experiments, you have to go to this paper here, which a lot of the sort of what I'm going to say will based on. Unfortunately, I cannot show their movies because nature will charge me hundreds of pounds to show it. So I can't. So you have to settle for this mimicry, okay? Because it's being recorded. But look something like this. It's not as neat as that, but you can go to that experiment and look. Now, so that's a confluent tissue. Are there any questions about it? Right. So what is a nematic behavior in a confluent tissue, right? So in a confluent tissue, it was kind of polygonal, but you can assign a shape tensor that basically elucidates the aspect ratio of a cell. And if it's elongated like that, we say this is the nematic director. And this in 2D, it just even responds characterized by one single number, the theta, the angle. And going back to the simulation, we see that you use some sort of coarse-grained kind of detection algorithm, and you will find, forget about don't worry about the blue dot and green dot for the time. Just look at the directed field, and that corresponds to the underlying tissue based on the cell shape. Again, I can't show you the actual movie, but that looks something like that for the real thing. All right, so yes, please. It is an active vertex model. It is a vertex model, yes.
And just active Brownian?
It is active Brownian, but it's not crucial to what I'm going to say. Just pretend that this is the real thing. It looks something like this. So it's like a, you can check the real paper, as I said. Now, so if it is well, let's assume that we've got some sort of nematic fields going on, and if there are no fluctuation whatsoever, and if it looks something like this, when you add a bit of fluctuation, so this is the directed field where I just connected all the bars, right? Now, if you have a bit of fluctuation, there will be some wiggling, more fluctuation, defect like this, where there's a singularity where you cannot define perfectly what the nematic director is, right? So specifically, what we see in these tissue models are two types of defects, something like this and something like this. We call this a -half defect for the following reason. Many of you are very familiar with that, but I'll go through that very quickly. We draw a circle around that singularity. We put an arrow, and then we just go around that nematic field lines by turning the arrows. And as you can see, after going around it once, the arrow has turned minus 180 degrees. So it's turned in a clockwise manner. And hence we call it a half defect, half because it's not a full turn, not 360. Now, in this case, because it's nematics, the fact that the arrowhead is pointing that way and that way is immaterial. We say they are the same. So it should be, you can imagine it to be a bi-directional arrow. So this is a -half defect. For the same reason, we do a circle, and then we just wind it around, go around the curve, and we get a 180 degrees half turn in a counterclockwise manner. Hence, this is a positive half defect. Right? So now we can focus on the blue dots and green dots using the detection algorithm used in the Nature paper. Then you can detect those plus defect, plus half defect, and minus half defect. Any questions at this point?
Maybe just to be clear, so
Yeah.
I suppose these red lines, they could also have a length, but they only have an angle.
Yeah, so here they only have an angle. You can add you can talk about the length as well. But what I'm showing is just the angle. The theory itself, nothing changed. Yeah.
What about topological conditions? For example, if you have some vertex.
Yeah, you'll see that. Well, you look at that, you can see annihilation and creation. Yeah.
Topological changes of the mesh. The mesh is not going to be
Of the mesh.
Of the mesh.
of the cells, right? Not on topological changes will be nematic.
Because if you have two vertices coming,
Oh, T1 transition, yes,
it
it can happen. That's a fluid, so it can happen. It will happen. And if you look closely, there will be T1 transitions. Yes.
Look at correlations between velocities and
Yeah.
nematic character.
Yeah.
And I must admit, with all of the stuff of all the things nematic part of the elongator is not.
Yeah.
You ignore the effect.
Yeah, well, the good thing is that I am using this movie as a cartoon. Everything I say is analytical. So that all these effects will be taken into account. Right. Any other questions?
Do you ever try evaluating the QIJ tensor, or is that how,
Yes,
another way? And so,
it,
I mean, this
it will come in.
doesn't look hugely pneumatic. I mean, normally molecules don't form a pneumatic phase unless I have to say about a 5:1 aspect ratio. So this looks more like an isotropic phase with short range
Yes,
correlation.
it's completely agree with you. Yes, that's that's our perspective also. Yes,
Okay.
but that is local nematic alignment,
Right.
short range. Sorry?
But I mean, for instance, you can measure a scalar order parameter, which gives you now a
That's
measure of
right.
pneumatic order. It looks pretty small.
We have scalar again. This is a cartoon. So don't it doesn't matter. It can be completely wrong. Doesn't matter. The analytical theory is correct. My perspective. So we'll get on with
You're
this.
just showing this because nature won't let you show that.
Exactly. Thank you.
You are the
I wish I could show the nature movies and then I can say, well, it's not my work. I don't.
You were the first speaker I've ever heard who said the copyright will stop you from showing something. So
Have you tried to get the permission to show movies?
for a dissertation, like things like
Yeah,
that, but I never.
For
think about it.
recordings,
For
I tried. The science allow you to do that. So I have that movie from the C. elegans. Science let you like give that permission for free. Nature doesn't. So take that into consideration for the next session.
Thank you.
Okay, so well, okay, they move around cells and now, if we forget about the tissue, going to a single cell level, renal cell is contractile in the sense that if you elongate it, it has a tendency to round up. I.e., if I put a cell in an elongated configuration, it's gonna pull to make it round again. Again, I can't show it because it's nature. There are many other experiments. No, it's not. Well, you try. It charges me for that movie hundreds of pounds.
I would like to see what happens to it anyway, but.
No.
No, don't try. Don't try.
So there's a recording of it. So,
Yeah, we can have that discussion of yes.
What you say is not true for all cells, right? I mean, our cells will have an elongated shape. They're
Yes.
Happy with that.
They would have a yes, if you but this is MDCK, but true, there are cells with a already an aspect ratio, but even there, if you elongate further, they will just go back to that. But yes, but here it is MDCK has this tendency, and we call it contract. Right. So if you put a bunch now, put all of them together back into tissue and form kind of like a plus half defect. Just looking at the force vector, you would expect this defect to move down, right? Just force diagram here. But that's not what happens. if you do this, again, real experiments are mimicking the real experiments. Yeah, people have done that in the Nature paper. They look at the plus half defect, they actually move up. Yeah. So why? That is the problem. Individually, so when they move up, it's as if, so from this collective behavior, one would conclude that the cells are actually extensile. When you stretch it, they make you stretch further. So why the disconnect? That's the conundrum here. At the cellular level, cells are contractile. When you put them together at the tissue level, they look like they behave like an extensile nematic. That's the problem. Right. Any questions? Okay, so what's the resolution? Our resolution is that what's missed out in that consideration is the fact that the cells are not just pushing against each other. It's not pure cell-cell interaction. And this is put on the substrate. We'll have cell-substrate interaction. Cell tissue crawl on a substrate. Clearly illustrated in this paper here, Physical Journal, Elsevier, also charges. Can't show that. Okay? Cell press. That's Biophysical Journal. And so if you take that into account, I'm telling you the resolution in words, and then I'm going to give you the mathematics, the physics. But here it's just words. The resolution is that cell tissue can crawl on the substrate. As a result, there will be polar fluctuation at the cellular level, because when you have a substrate that can move on the floor, and there will be a polar monopole kind of force. But if you don't, if you just talk about cell-cell interactions, then you can only have this nematic interaction. As I said, you have two astronauts. In space, the only way to move is to push against another astronaut. You cannot swim, not even because there's no air. But if you are on a substrate, then you can have this polar interaction. When you take that into account, you will generically encounter extensile behavior. You expect extensile behavior at the tissue level. So there's a related paper here, first of in the audience. So that's if you're interested, go have a look at that. So basically, that's our resolution. Now, so let's fill in the detail. Yes.
But then you introduce another orientation order parameter that doesn't need to coincide with the shape order parameter.
That's right. That's right. That will be the velocity thing. Yeah. So universality of teaching. So for people who do like us, right, who do biophysics, that's the question that we have to answer all the time. Biologists will say, how could you possibly model that? There's so many parameters, right? Well, our perspective, my perspective from physics, of course, there's no difference in physics to talk about air density or air pressure. There are many different gas molecules in here, but we can do it. Thermodynamics can do it. So the perspective is that even though microscopic dynamics can be complicated, the underlying symmetry and conservation law can be simple, and that can lead to a universal hydrodynamic set of universal hydrodynamic equation of motion. So that example is Navier-Stokes equation. Now, I think we are so used to the Navier-Stokes equation, we forgot how miraculous it is. There's only gas, oil, water, whatever fluid. And in fact, if you say you do fluid mechanics, in fact, you are solving Navier-Stokes equation. That's how universal it is. So now, how do we use symmetry consideration to derive the Navier-Stokes equation? Now I'm going to derive the Navier-Stokes equation. And I hope it will be the quickest derivation of the Navier-Stokes equation you've ever seen. So let's do the incompressible limit for simplicity, but you can do the compressible limit. The first thing to do is to identify what we are looking at. Because it's incompressible, I don't have density field, I only have the velocity field. Okay. So I do dynamics. So all I need to know now to write down the equation of motion for simple fluids is del V by del T with some force that I don't know, right? But again, reminding us there's a divergence-free constraint because we are talking about incompressible fluids here. So we have to know what F is. How do we determine F? Well, That's the question. Well, we use symmetries. What do we know? F cannot depend on time. If you do experiments on Monday, it cannot be different from on Tuesday. So it cannot depend on time explicitly. It cannot depend on location. It cannot depend on rotation. There's no magnetic field that takes out. We're not talking about magnetic fluid here, simple fluid. There's no chirality by assumption. You can add that in, but we don't make that assumption in another. We don't assume that it's broken in another Stokes equation. And importantly, we have this Galilean invariance. So what do we do now? Right. So let's do now. It boils down to an undergraduate first year exercise of vector calculus. Right. So I have this here. I've got a vector on the left-hand side. I have to map it onto a vector on the right-hand side. And F, for the first here, terms like this will not be allowed. Right? This is not allowed because I've got explicit T. Translational invariance disallow terms like this going into the F, explicitly position. Rotational invariance disallowed terms like this going into I do 3D, so a term, sorry, I guess I do. So a vector alpha cannot go into F, right? Chirality, i.e., I cannot have an antisymmetric tensor. This is not allowed. And then Galilean invariance is more complicated, but we'll come to that. But now, what terms are allowed? Well, terms like this are allowed. I just have to, it becomes a matter of contracting indices, right? I can have this. Right, well, is your imagination you can write down all possible combination. You can write K, BK, VI, right? All possible combination. Any other suggestion? Let me add the effective term, which is allowed, because we do have that, right? We have terms like this, right? So if you write down all the terms and then just use Galilean invariance miraculously, that's the only term you have. Every term, going back here, this term, I've got I can have terms like this, but this is not allowed because of Galilean invariance. It picks out a substrate, it picks out a particular variance. That's not allowed.
If I put it that way, why wouldn't the other ones pick out that are in the frame, like the second?
Which one?
Like the convective term?
Yeah, it doesn't, because you actually need that when I do a boost.
Yeah, okay, yeah, it comes out.
I need that. And in fact, when I go back, all of these terms can have a prefactor that's arbitrary, right? Well, if you, so in principle, I could have a prefactor lambda, but because of Galilean invariance, it has to be 1. There's no other possibility. And what's missing, you can say, well, this term is in fact allowed. This is allowed, right? In fact, Laplace into the 6 to the 8, as many higher powers as you like, will be allowed. But we are doing hydrodynamics. Hydrodynamics means that we are going into K goes to 0, omega goes to 0, large length scale, large time scale. So this term will be irrelevant compared to this term. That's why in Navier-Stokes, we never consider that term. But if you are doing super high speed, simple fluid, you bet this term will come in, because when at some point Navier-Stokes is going to break down when microscopic dynamics becomes important. And also here, sorry, I wrote over that. This is what we call pressure. It's just a Lagrange multiplier to enforce the incompressibility condition. We can put it mathematically, it's just a Lagrange multiplier. Physically, we call it pressure now for incompressible simple fluid. So that is the derivation of Navier-Stokes equation in the incompressible limit. Based purely on symmetry, you don't need to worry about what stress tensor is. That's not easy, right?
Sorry, it's not only based on symmetry, it's based on symmetry plus timescale. And this is crucial. No?
This is hydrodynamics. Yes.
It's symmetry plus timescale. And we could
agree.
whether it's there.
Yes,
clearly there.
I agree with that.
And also SPL, I should say.
Yes, yeah.
So also, yes, so completely agree. And also the Bayesian norm, if you are doing. And you have an additional continuity equation that's conservation law. Here has no momentum conserved, but at this hydrodynamic level, let's give you everything. Right. Okay. Right. So now let's do the same with confluent. Right. What are the hydrodynamic variables? What are we looking at experimentally? We're looking at velocity field. We're looking at nematic field. Now, why do we introduce a nematic field here instead of keep using the directed field? From this symmetry consideration, so that's the scalar order parameter S. That's crucial. Now that's the nematic sort of unit length vector. Well, the reason to introduce Q is because, well, for symmetry consideration is simpler because the symmetric is traceless, 2x2 matrix, so it's much harder to work with N because then you have to worry about this double counting N equals minus N, so Q does that for you, right? So we do play the same game. What are the equation of motion here? Well, I say this is still an incompressible tissue, it doesn't matter. It works for compressible, but let's keep it simple. I have this A, and then I've got a dynamical equation for Q. I've got this B, arbitrary. B is symmetric and traceless because Q is, right? So, same symmetries as before. There's no Galilean invariance because they're falling on the substrate. So what kind of equation you get? At the linear level, which suffice, I'll tell you why, but why linear theory is okay, but let's write down the equation. This should be, I've already set it to del V by del T to 0, but imagine del V by del T. This is all the equation, all the terms you can get at the linear level. There cannot be, there are no DQ coupling because it's nonlinear. Questions?
Yeah, I too, it's not almost philosophical question.
Yeah.
So here we go, yeah. The first one is about separation of length in time scales. And I would argue in something like one of these, especially in these cases, should be look at these like the scale of X3 cells, this is questionable. Yeah.
Yeah.
And the second one is what happens to polar active problem motion? Is it just because when you have divergence of things in here, shouldn't there just be a plane
Polar with alignment or without alignment?
without alignment?
But without alignment.
Yeah.
So
And if you say,
yeah,
no, this
it's a bit like this. Yeah.
if it disappears at larger length scales, maybe it's true, but we know that larger length scales.
Yeah, I think yeah. So that ultimately has to come back to the experiment and say, are we at what length scale? It makes sense to talk about local nematic order, right? Yeah, I agree with you. Any other questions? Right. So linear theory suffice, and also importantly, look at this damping term here. I put in a damping term. That's why I can set del V by del T to 0, right? Because this I've got damping in V, damping in Q. What it means is that there's no collective motion, which clearly it doesn't. It cannot. There's a boundary here. So this is you must have a damping term. I guess physically you would expect a damping term anyway on the substrate. And then there's also a damping term in Q because we don't see long range nematic order. So we do see local nematic order, but the fact that it doesn't have long range nematic order means that it is damped. It is in the, in other words, it's in the disorder phase. It's not in the nematic phase. Yeah.
There should also be a convection term, right?
No, B dot B is not linear. So this is linear. Linear theory suffices because both V and Q are small. That's fine. So we can argue whether experimentally in the experimental system is it linear theory matters, but analytically I can tell you this is the universal model of confluent tissue, at least at the small fluctuation limit. For the same reasons, Navier-Stokes equations are the universal model for simple fluids. Okay. Well, okay. So now the point of polar fluctuation comes into this term here, right? Without this term, then you will have everything. Also, you still have velocity because they move around. But if you are doing experiments on a floating kind of frictionless membrane, then you cannot have this term because it's a false monopole. It goes into the velocity. So this is this account for cell substrate interaction and is of this form generically, right? That question.
Yes, sorry, just me again, yeah.
No, please.
If you do this with active particles and do sort of small linear elastic or even
Yeah.
calculation
Yeah.
with this other system, you can get that kind of noise, but with a spatial correlation, right?
You can add spatial correlation also, but here the thing about hydrodynamics, which is a bit of a cheat, is that well, I can have spatial correlation, but hydrodynamic means I'm taking the infinite length scale, so every spatial correlation becomes delta in that limit.
If you're trying to describe the effect at the scale of 4 cells,
You may again, so you're saying maybe hydrodynamics may not make sense. I agree with you. It depends on the experimental system. Any other questions? Right. Okay. So, right. But also, what I didn't tell you in this equation, because you're writing down all possible terms, you write down terms like this, which you cannot do if you don't have cell-cell active interactions. Because if you don't, this is an active term that's only allowed because the cell can push against each other in an active manner. If you don't have that, then you will use you will differentiate, you will have some differentiation of the Frank free energy, and you will have some high order derivative of Q coming in. So it comes in here as in this manner purely because this is active. And if you allow, which we know cells push against each other clearly. So if you allow that, you have to allow for active fluctuation as well, which is of this form. Slightly more complicated, but ultimately it looks like this purely because Q is symmetric and traceless. So you need to have this thing in here and you check it and it makes your noise term symmetric and traceless. But ultimately it's the same idea. I've got a polar fluctuation for V with strength lambda, and I've got active nematic fluctuation with noise strength lambda Q. Any question? Yeah.
So do you have one sample symmetry so get one sample top?
No, there's no. Good question. It doesn't matter. It's an active system. I don't need that. It may or may not respect Onsaga symmetry. I don't, but it shouldn't. It's an active system. There's no reason there's any equilibrium thing going on. Yeah. Any other questions? Right. Okay. So now with that equation, ultimately we have to use it. This is my universal model now. Well, by doing this from symmetry, of course, I don't know what these numbers are. No one knows, except experimentalists who can actually measure them. But for stability reasons, I know these have to be positive. Otherwise, the system wouldn't be stable, right? Now, and lambda has to be positive. This is the flow alignment P factor, which you expect to be positive. But it's positive because if you're stretching, if you are stretching a bunch of cells, of course you expect the cells to be stretched out in the x direction. And for that reason, lambda has to be positive. If there's a gradient in V, Q has to follow in the corresponding way that you would expect physically. Right. So what I'm saying is pretty much the only physics here, right? Before it was all first year undergraduate mathematics, this is the physics. Yeah.
You said that the gamma term is an active term. So why do you
Yeah.
expect
Alpha is active. Alpha is the active term. And then this omega
but
is
gamma couldn't just describe the
gamma, which gamma? This gamma. Oh, this is not active. This is just damping. No, that's no, you don't need, okay. You can, yes, you're right. This outside can be thermal too, but you need cell substrate interaction. Otherwise, it's not allowed because you cannot push against nothing. The fact that you have a force monopole in the velocity means that just for the same reason that I can move, right? But if I'm in space suspended, I cannot move forward on that one. That requires substrate interactions. Okay. We can discuss it further. Yeah. So right. So how about finally what is alpha then? This is the crucial thing. In fact, that determines whether the system macroscopically, collectively, is extensile or contractile. If, well, here is a little proof, but I guess it's too fast anyway. So if you think about Navier-Stokes and you go back to the usual derivation with a stress tensor, and here you treat this as a stress tensor, which goes like alpha Q, then basically when alpha is positive, it means that the cell is contractile. If alpha is negative, it means that it's extensile. But in the active nematics literature, basically that's what it means. What the sign of our alpha dictates whether it's extensile or contractile, also dictates whether the plus half effect will move in a particular way. Okay. Now for MDCK cells, again, as I talked about, at the single cell level, it's clearly contractile. So we expect alpha to be zero, greater than zero, right? So how do we resolve that? So why do we see extensile behavior at the tissue level? Well, the reason is that there are many other terms, and when you do experiments and then you look at defects, effectively, you are looking at an effective alpha here. This gets renormalized by all the other terms. It's as if you do a QED and you ask this mass of an electron. Well, it's not going to be the bare mass, it's going to be other photon electron interaction QED, and then you get renormalized. Here, it also gets renormalized. Not just for the magnitude, the sign changes. If you do, this is now a linear theory, so everyone can do. Slightly more complicated. Go to Fourier space, it becomes a algebraic problem to solve the eigenvalue. But this looks complicated, but it's nothing more than maybe an upper year undergraduate course. Yeah, so that is the correlation between V and divergence of Q, which effectively is calculating this alpha effective. That is quantifying at a tissue level when you don't care about anything else, whether that tissue is extensile or contractile, and you give this number. And remember that this is the cell substrate noise strain. This is the cell contractility noise strain coming from, that's cell-cell interaction, that is cell substrate interaction, okay? This term is always negative. This term is always positive. I.e., if you don't have cell substrate interaction, it will forever be contractile. At the tissue level, it has to be contractile. If you have substrate interaction strong enough, then it becomes extensile. That is the resolution. Okay. Any questions at this point?
You said that this is the top blue box is already on the hydrodynamic scale, but then you say, well, alpha has to be the sign it is because of what the cell is. So,
because here, when you look at when I analyze the data, I treat it as if it is you only have V and divergence Q, and I ignore all the substrate interaction, mu and flow alignment. Right? So then you have to renormalize this alpha accordingly. Because effectively, I'm claiming that experimentally, what we are looking at when we talk about extensile versus contractile behavior is this correlation.
but when you say renormalize, are you talking about PR transformation, or are you talking about integrating out the Q, for example? I mean, what kind of
It is integrating out everything because it becomes a number now. This is an equal time, equal distance correlation. So everything is integrated now. I'm just doing a correlation. Now, conversely, when I analyze the data, I incorporate, for example, if I incorporate this term in there, then I subtract it off from this correlation, I will conclude that, well, cellular level, yes, they are contractile because after subtracting this term, it is indeed positive. So the fact, in other ways to say, is experimentalists didn't subtract off that effect on this correlation. That's why they conclude it is extensile.
I think.
Thanks. Any other?
So lambda, I think lambda has a physical meaning, which is the flow alignment.
Yes, that's right.
So you can kind of, estimate what lambda is.
Oh, it's positive. All I need is the sign. Oh, but you're saying,
is it enough to give the sign?
now there are experiments where they weaken the cell-cell junction contact, and it does, the tissue becomes contractile. Let me, well, maybe that's not a good example because I don't remember exactly. So let's say I take that back. I don't remember the experimental pattern. But what's your question again? Sorry, you're saying be more quantitative than just determining the size.
So lambda has this community.
Yeah, that's right.
Share.
Yes.
Say a rod shape. One of the
That's right.
line that's something.
Yes. Yes. Yes.
You know what lambda.
Well, I don't know what the actual number is. I know it's positive
But
for that exact same reason.
Yeah.
That you stretch it, it's going to stretch.
So when they run out of food and they can't move anymore, is the parameter that goes to 0 come down?
Yeah. Maybe large we can do the experiments. I don't know. Lambda is not active, it's purely passive.
Which parameter goes to 0 when they're dead?
When they are dead,
They have no food.
this alpha goes to 0, omega goes to 0 also. So that's another interesting thing. When you don't have fluctuation here, it's inconclusive. You don't even have that term. That's another kind of, this is, I would say, quite interesting thing. You cannot get contractile motion by just having active alpha. You need noise too. Well, partly because I'm just calculating a full correlation function. If you put that in the wave number, maybe that the conclusion will be modified.
Okay, and when you have traction forces, you lose conservation of momentum. Is that
Yes, that's right.
By the way, a bird was just trying to fly in that window, so we almost had some active matter. I saw it flapping in the air was there. So you never know what might come out.
But birds are different from pneumatics. So that's polar active pattern.
So, correct if I'm wrong, if you have number of hydro experts in here. So if it's long and thin, it tends to be positive. If it's short and fast, it tends to be negative, right?
Well, that's different here.
Yes.
Yeah.
Yes. So
So the thing I wanted to ask, and the cell is deformable, right?
Yes.
So it can be either what do we move on sort of flow line and part?
no, you do well. Here's the proof, right?
The orientation that you're talking about, but not the length.
It's more than the reorientation. In passive pneumatics, the shape doesn't change, so it's that's harder to even visualize. But here it's much easier purely because the shape changes. If I have a extent of shearing speed, i.e., it keeps on going faster and faster in the x direction. Of course, you expect a certain stretch, right? And hence, lambda has to be positive. You don't even have to worry about the angle between the flow field and the pneumatic crystal with a fixed length. Here is the shape changes before. I guess one way to say it. Of course, at the hydrodynamic limit, I cannot say anything about the microscopic details, but I would say here the shape changes before it even rotates.
Yeah, I thought it's interesting. I saw meeting where radiation about people that's deformable.
Yeah.
Vibrated things, and they show repeatedly similar behavior to the cell.
Oh, good.
Yeah.
Great. Excellent.
What was that?
Radiation chemopathy. I don't think it's published in a story and stuff.
Okay. Thank you. Right. So that is the resolution, right? So okay. So now we can go further. This is really add on. Okay, compressible tissues. I have that incompressible constraint. So what are the new hydrodynamic variable density field? That's the only thing new. You write down as before a linear set of at the linear level a universal set of equations. Same analysis, same conclusion. You can go to my paper and see that. You can do active solids. No T1 transition, everything's fixed, like a matrix with strains. Right? What are the hydrodynamic variables? Displacement field, pneumatic field. Right. But universal equation at the linear level, same analysis, same conclusion. Okay, polar fluctuation always leads to extensile behavior. Okay, so that's yeah, please.
When you say pneumatic solid,
Yeah.
why do you take into account the displacement field? What exactly the displacement field?
It is, if you give me a reference frame when they're dead, and they move slightly from that reference point, every cell, center, nucleus, when you add ATP to it, they move. It doesn't work like that, but let's say you switch it on and they start moving, and the nucleus moves away from that reference point, that is the displacement vector. Okay, so that's all I wanted to say. Now, a quick summary. What was the problem? There was a disconnect between microscopic contractility and macroscopic extensile property. The resolution extensile dynamics comes from cell substrate interactions. I demonstrated it using, I claim, the universal theory of confluent tissues from symmetry consideration alone. And the conclusion applies to other slightly more complicated system. Now, I would like to end with a broader perspective, right? What I've done here, right? Drawing back to this universality in biology idea, right? So, beyond tissues, the first thing to do again is to find out what experimentalists are looking at. That would be your variables or fields of interest. You then, from there, start taking into consideration, you ask the biologist, what are the symmetries that they expect to be satisfied? They may say, oh, chirality is not respective, and you add chiral terms in there. That will give you a universal model equation. It is universal because you capture everything, right? It has to be correct because you have every term possible allowed by symmetry. But that is not tractable with infinitely many terms. So typically you then say, I do hydrodynamics. I go to large length scale, many body problem. And that led to a dramatic reduction in model parameter. Think Navier-Stokes equation. In the incompressible Navier-Stokes equation, there's only one parameter, viscosity. The plane fly through air, assuming it's incompressible, to a whatever surfboard on water, serving of water. There's only one parameter that distinguishes between them, assuming in the incompressible limit. That is a dramatic reduction in order parameters, which renders the model itself tractable. And then from there, you put in some biophysical inputs. I mean, the defect, of course, is that I don't know what the numbers are, but if you're lucky enough, you only need the signs, then you can come up with some meaningful conclusion. Thank you very much for your attention.
Thank you. Different questions. Maybe I'm asking, I'm not sure if it's the right question for us, but if you, in your hydrodynamic equation, in principle, you will compute spatio-temporal correlation.
Yeah, that's right.
But what you showed was just spatial correlations in infinite time.
It is equal time, equal space correlation. It's even, there's no wave factor. Everything's integrated now. No time, no space.
It was also a large time limit, right?
Yes, well, the large time limit is already implicitly taken because I work with the hydrodynamic equation.
Sorry, can you go back to the?
Yeah, of course. You are talking about.
Yeah.
Sorry, I think here or here. Oh, yeah, you're talking about the this here. Yes,
yeah.
Yes.
So here the left one.
Yeah.
That's
so times there's no time also. Okay,
right.
sorry.
So it's the last bit. Yeah.
Because because of the damping, del V by del T is gone.
Okay.
Time's gone anyway. Equal time, so it's equal time, and then it's equal space because I integrated out all wave numbers.
What I was wondering is that usually in these kind of things, how do you connect the regime of validity in the sense that suppose I let these systems evolve, eventually let's say some of these fields become big, and typically nonlinear terms stabilize this system.
Yeah. Well, nonlinear term, who can do nonlinear term? The only systematic way to deal with nonlinearity would be to use the normalization group method. That will be, as far as I know, the only way to probe what happens with nonlinear term. Of course, it will be very interesting, and it can be done in some cases.
I mean, that's a
Numerically, yes, of course. I mean, yeah, clearly, numerically, you can do that. Yes.
But in these kind of systems,
is all about. So yeah.
sorry, so in these kind of systems, people have not thought about adding nonlinearity.
There are people who do nonlinear stuff. Sure. Yes. But here, what I said applies certainly in the linear vision.
Okay.
Yeah.
So, in terms of your broader perspective, the last slide.
Yeah.
Have you thought about the following? Because people have raised, great questions about depending on what length scale and what time scale. Maybe you might have other terms, or maybe the theory doesn't quite look like this. In the sense of biology, is much cleverer than we are. So I asked that, I posed that because there is work done by Ahmad Borzu, myself, and Ali Tallison, and then also, I guess, Jorn Dunkel had a similar paper where we basically say, let's use the experiments. Let's do the experiments or run the experiments, and then have some general universal, all the terms that might exist, symmetries or whatever, maybe because the cells alter, given all their internal mechanics, they decide to change a different type of cell, and then maybe a new symmetry arises or arises. And so you watch over time, and then you have a fitting, if you will, a data. So fitting the experiments tell you what the equation is, so that you have coefficients associated with each term. And then watching over some time and over some length scale, you can sort of back out what those coefficients are. And then you can go and say, all right, maybe there's some hand waviness, and now at least a data-driven approach to letting the data tell us what the theory is. And then we can go forth and use our, take linear approximations and then find an effective alpha, so that yes, actually the effective alpha is this sign versus the bearer has that sign. So have you thought about doing something like that?
Well, machine learning, I guess.
Well, I mean, machine learning, whatever you want to call it, but yeah.
Right. So learning from. Well, I guess yes. I did some of machine learning on. Well, that is specific to defect detection. So that's very specific to a particular. It has nothing to do with that. Well, it's just detecting defects in either from a movie. Right. So that's sort of learning from the data. No, I think it's very worthwhile. Not in my agenda to sort of approach it like that.
Also,
So it's really a European question earlier. So normally when we talk about defects in nematic, right? Usually you are in the nematic phase. So
yes,
the nematic order parameter is large. And then when you have defect, the nematic order parameter drops. And the defect one, and then goes up again when you have defect. So basically the experiment that she showed me in the beginning, the order parameter is basically 0, which are in this order phase plus.
No, locally it's not 0. Locally it's not 0. Globally it's not in the nematic phase. Local, that you can have no local nematic order, very long range. Well, not long range, but very large length scale nematic order. May not be true experimentally, but in this theory, that's the question is, does it even make sense to talk about Q, right? Well,
I mean, does it make sense to talk about defects in the Q?
It does, because I can have very large length scale correlated Q field. It's like the Ising model. In 1D, you wouldn't get a phase transition, but if the temperature low enough, you can have very long, large length scale correlation. Then you can talk about magnetization within that length scale.
Okay, that's like in Ising model in 1D,
yes,
or dimension. So you have this defect, which is what we call it the
domain wall. Yes, but
yes.
Yeah.
So you know that it's clear that you have defects in nematic, like a domain wall is one such is you have +1, the other side is -1. But then it is nematic defects that we are talking about in the production. Or the parameter, which is basically 0.
No, it's not locally. It's not 0. Globally, it's 0. Locally,
how do you know it's? I mean,
well, because otherwise, all you need to define a defect modulo that particular algorithm of defect detection. All you need, you do a winding number. As long as locally you can see it is more. Okay, let's say this patch, more or less a line.
Average over is
your average of
cell,
something like that. Yes.
You operate for 5 cell. It looks like the average almost.
Now, I mean, again, right? Largely, I don't want to put you on the spot, but I'm just reporting what they have a robust defect detection algorithm, and they use it and they detect defects. as long as you have a, but ultimately, as long as you have a local Q field, that makes sense, then you can talk about defect. If you don't even have a local Q field, you shouldn't have, you wouldn't have Q anyway.
Yeah, so ask personally then.
Yeah.
Do you think it should be fitting a defect in it?
Yes, I think so. I think it works. I mean, we tried, right? We were, but when we started doing this, obviously inspired by the Nature paper, it's very robust. We do the active vertex simulation.
Would be the object, say robust, then remember correctly, you need to pause for in the space.
Yes, that's right. Cross grain in space and time.
Is it robust to use the entire scale?
Yes. Yes. Well, of course, you need to be big enough, but it is not fine-tuned to get you defect. So that's clearly not the case. It's not fine-tuned to, it's not a cheat to get defect. The defect does exist if you, and then you define the robust detection algorithm, you'll get them robustly. So I think it's genuine, and I think the whole analysis is appropriate.
So I don't understand all that. So let me just ask. So you're saying that on the level of the signal set, it is contradictory.
Yes.
And then there is a microscopic an interaction between the cells.
Yeah.
For a group of cells and the substrate.
That's right.
And that's on a different length and time scale.
No, they're also microscopic.
Which is leading to extensile behavior.
No, everything's microscopic. The only thing you need is a microscopic cell substrate interaction that immediately takes you to that transition from the method to, if it's big enough, if the cell substrate interaction is big enough, that overwhelm that contractile terms, then you expect extensile behavior.
There must be a crossover length.
Yes.
That's what I don't understand.
Well, it's not a length scale. It's a strength crossover, right? I've got this negative term, I've got positive term. If this term's bigger than that term, it is extensile. It does not depend on length.
I am, let's say, I'm an experiment.
Yes.
I'm not, but
Yeah.
I've got one cell.
Yeah.
It's contractile.
Yes.
I take two.
I see what you're saying. Well,
Yeah.
you're absolutely right. I see what you're saying. You're saying, how big a system do you need to get this transition? As big as it takes for it to make sense to talk about the Q field. As big as it takes for it to have defect appear. I don't know when it will appear. I don't know if the defect will have some sort of length scale, like the separation, the density of defect. All these questions will be non-universal. It will be very model specific. But I'm saying if you're big enough to see defects, then you will get this transition. I don't have to talk about defects. I can talk about the flow pattern stress field around. It is purely because experimentally people use defects as a proxy for the discussion of whether it's extensile. Yeah, that's effectively what they are doing. So yes, I think if they do that, then it's much clearer. They don't have to look at defect, they just have to do the absolute. Yeah.
May I actually step back and ask you, but I don't think learning any biology, right? Because this is fantastically interesting physics, right? But does biology care?
I think so. I think it's very crucial in a biological setting because we basically, it has highlighted the cell extra ECM, for example, interactions. They're floating, like a developing embryo floating on a frictionless space should behave differently from to planar tissue on a substrate. So that is biological, that can be biologically relevant. I would say.
What you say, I actually agree with you that these things emerge because I suspect there's more than one way of getting the result. If I'm looking at the result here, you can split the sign with full alignment than any of the other. It's gamma, there is V, there is beta, and even Einstein's delta again, right? There's more than one way of switching it.
Yeah, but then we do have physics here. We do have. So this is the only sort of biophysics, right? These signs you cannot flip the signs. These signs are fixed. If you flip the signs, these equations don't work. If you flip mu, then you need a Laplacian
Yeah,
form.
I didn't read the sign.
Oh, right.
I meant the relative values.
No, you cannot. No, well, okay, the transition point, yes, but the message is still the same. If you don't have cell substrate interaction, you will never get extensile.
Anyway, I forgot.
Probably stop.
Right.
You can again.
Okay, thank you.